Hello and welcome to section 5.7. Today we're going to look at graphing and solving quadratic functions. By the time we've completed section 5.7, we should be able to graph inequalities in two variables and solve quadratic inequalities in one variable, and then be able to apply these methods to real-life applications. Before we get started, I want you to think about what an inequality is. And if you recall, an inequality pertains to the less than, greater than, less than or equal to, or greater than or equal to functions and symbols. So because we're dealing with quadratic equations, we're actually going to look at quadratic inequalities. So I'm going to have something like y is less than ax squared plus bx plus c, and so on. Now when we go to graph these, we also have to remember that when we graph, we're going to have to use a solid or a dashed line. These two right here will produce a dashed line. And these two right here, because of the less than or equal to piece and the greater than or equal to piece, these will produce a solid line. And then we also, with inequalities, have to shade. And we're going to either be shading the inside of our parabola or the outside of our parabola. We do have a few guidelines when we're graphing quadratic inequalities. And the first thing we're going to do when we go to graph these is we're going to draw our parabola, and it has to be in the form of y equals ax squared plus bx plus c. So once we know what the shape of our graph is going to look like, where it's going to fall, and so on, we're going to use a dashed line for inequalities that are less than or greater than. And then we're going to use a solid line if we have an inequality that consists of a less than or equal to or a greater than or equal to. Once we've done that, we're going to choose a point, which is going to become our test point. And I typically will choose a point that's inside of the parabola, and we're going to check whether or not it's a solution. If it is a solution to the inequality, or if it makes the inequality true, then I'm going to shade on the inside. If this point does not make my inequality true, then I'm going to shade on the outside of my parabola. So let's go ahead and take a look at a couple examples. So example 1 says to graph y is greater than or equal to x squared plus 2x minus 4. Now because this function is not factorable, I can at least calculate the coordinates of my vertex. So my vertex is going to come from solving for my x coordinate first. And with that, I know that x is equal to the opposite of b divided by 2 times a. So that's going to give me an opposite of 2 divided by 2 times 1. And when I simplify this, I get a negative 1. And then I can solve for my y value by plugging this negative 1 in to my original function. And I end up with a negative 1 squared plus 2 times a negative 1 minus 4. And when I simplify that, I end up with 1 minus 2 minus 4, which will give me 5. So the coordinates of my vertex are negative 1, negative 5. This is something I would expect to see on your tests, quizzes, and homework. So now I'm going to assume that each interval on my graph is a unit of 1. And I'm going to go ahead and plot my vertex at negative 1, negative 5. So I get a point right there. I can quickly calculate my y-intercept because I know that if I set x equal to 0, I can solve for y. So y is greater than or equal to 0 plus 0 minus 4. So I have the coordinate point 0, 4. And if I finish graphing the rest of my function on my calculator, I see that I have an x-intercept at the point 1.236, so somewhere between 1 and 2, and a negative 3.326, so somewhere between 3 and 4. So now that I've shown my x-intercepts, my y-intercept, and my vertex, I'm going to connect these right here. And I'm going to double check. I have a greater than or equal to symbol, which tells me that I'm going to have a solid line. And then the next thing I have to do is I'm going to have to pick a point as a test point, which in this case, I'm going to pick the point 0, 0, and I'm going to plug that into my original function. So if I plug 0 in for y, is 0 greater than or equal to 0 squared plus 2 times 0 minus 4? Or in other words, is 0 greater than or equal to a negative 4? And the answer is yes. So because that test point was in the inside of my parabola, I'm then going to shade the inside of that parabola. So the graph of my quadratic inequality is going to look something like this. Next is example 2, and this tells us to graph the system y is greater than a negative x squared plus 3, and y is less than or equal to x squared plus 2x minus 4. I'm going to start out by graphing y is greater than negative x squared plus 3. And I know that my parabola is going to be an upside down facing parabola, and it's going to have a vertex at 0, 3. So I'm going to go ahead and plot that. Again, I'm going to make each point an increment of 2 or increment of 1. And when I graph negative x squared plus 3 on my calculator, I am going to, or I see that I have x-intercepts between negative 1 and negative 2. So somewhere in here. And I have another x-intercept between a positive 1 and a positive 2. And because my graph, this is a greater than inequality, this is going to be a dashed line. So something that looks kind of like that. Likewise, I'm going to now go and graph the equation y equals x squared plus 2x minus 4, which we just got doing in the last example. That is going to be a solid line, and we have a vertex at negative 1, negative 5. We had a y-intercept at negative or 0, negative 4, and we had an x-intercept somewhere between 1 and 2, and 1 in between negative 3 and negative 4. Again, this is going to be a solid parabola. So then I now have to go ahead and finish my shading. So because 0, 0 doesn't fall on either one of my graphs, I'm going to go ahead and use that. So when I plug that into my first equation, I have 0 is greater than a negative 0 squared plus 3, which gives me 0 is greater than 3. This is not true, so I have to shade outside of that function. So I'll get something like that. Then I'm going to do the same thing, except I'm going to plug 0, 0 in for my bottom equation, and I get 0 is less than or equal to 0 squared plus 2 times 0 minus 4, which gives me 0 is less than or equal to a negative 4. And again, that is not true. So now I have to shade on the outside of my blue line, and I'm going to get something that looks like this. Now it has to stay outside of the red as well as the blue. So what you'll notice is our overlapping region is going to be kind of right here and in this direction. And we're going to follow the blue line up to the red line. And it's going to be everything out here in this region. So this is where our solutions are going to be found. In order to solve quadratic inequalities in one variable, we're going to first look at the graph and solve ax squared plus bx plus c is less than 0, or it could be less than or equal to 0. And what we're going to do is we're going to go to our graph and we're going to find the x values that fall below. Because if this equation is less than 0, this is going to give me negative values of that function. That's why I'm going to look below my x-axis. Now, if I'm dealing with this equation here that has the less than or equal to, I'm going to look at points that fall either below or on the actual x-axis. But I can't include the points on the x-axis or on the graph when I'm dealing with this one because I don't include the graph itself. Same thing for when I'm looking at this equation and it's greater than 0 or greater than or equal to 0. However, when it's greater than or greater than or equal to, I'm either going to look at the points above or on and above. So example 3 says that we're going to solve the quantity of x squared minus 4 is greater than or equal to 0. Well, first of all, when we solve, we know that we have to end up getting x by itself. And I notice that I have a difference of 2 perfect squares. So that means I can factor this into x minus 2 times x plus 2, and this is going to be greater than or equal to 0. Next, I'm going to set each factor equal to 0. So I have x minus 2 equals 0, and I have x plus 2 equals 0, and I'm going to solve for x. So my two x-intercepts are going to be 2 and negative 2. And I can go ahead and plot those right now. So if I'm at 2 and negative 2, and I'm going to make my graph, my x-axis is going to go in units of 2. So this is 1, 2, 3. Likewise, this will be negative 1, negative 2, negative 3. And for my vertical axis, I am going to keep that just in units of 1. And I can plot my x-intercepts. We set our x-intercepts. We're at positive and negative 2, so I have one here and one here. I can calculate my vertex. My vertex is going to be found by taking x is equal to the opposite of b divided by 2a. And in this case, I don't have a b value, so I'm going to plug in 0 divided by 2 times 1, which gives me 0. So then when I go to solve for y, I end up with 0 squared minus 4, or y equals a negative 4. So my vertex has the coordinate points 0, negative 4. So my graph then is going to look something like this. And now I want to solve for when my graph is greater than or equal to 0. So I'm going to still select that test point, and again I'm going to use 0, 0 because it works out nice. So 0 squared minus 4 is greater than or equal to 0. So I end up with negative 4 is greater than or equal to 0. That's not true. So that tells me I'm going to be shading outside of my parabola. And because I want values that are greater than or equal to 0, I only have to shade the outside up to the x-axis. So what that tells me then is my solutions are going to be for values of x that are less than or equal to a negative 2, or values of x that are greater than or equal to a positive 2. So this right here is the region that's greater than or equal to 2, and this right here is the region that is less than or equal to negative 2. And if you'd like, you can always select a test point to confirm what you just solved for algebraically. So example 4 says that we're going to solve x squared minus 4, which is greater than 3x. And you can solve this using the exact same method that we did in the previous example, or we can use just a number line and help us solve that way. So the first thing we have to do, though, either way, is we still have to get this in standard form. And to do that, I'm going to subtract my 3x and put it over on this side. So I have x squared minus 3x minus 4 is greater than 0. And now I'm going to create a number line. And if I factor this, which it is going to factor nicely, I see that I have x minus 4 and x plus 1 as my two factors, which tells me that x equals 4 and x equals negative 1 are my two x-intercepts or my critical values. So I'm going to put those on my number line. So when I plot these, I'm going to plot, and it has to be an open circle because of this inequality symbol, because that's a greater than symbol, not a greater than or equal to. I have to include my point on my number line as an open circle. So I have an open circle on 4, and I have an open circle on negative 1. Then the next thing I'm going to do is my two critical points actually subdivide my interval into 3 intervals. I've got this interval, and this interval. And the intervals here on the ends, both are going to continue on. I just happen to stop them at negative 3 and 6, but they do continue on. So now I'm going to pick a test point from each interval, and my test point here, I'm just going to pick is negative 4. Then I'm going to pick 0 in here, and I'm going to pick 5 in here. So when I go and I plug those test points into my equation right here, I end up with a negative 4 squared minus 3 times a negative 4 minus 4, and this has to be greater than 0. So I end up with 16 plus 12 minus 4 is greater than 0. 16 plus 12 is 28 minus 4 gives me 24 is greater than 0. I'm going to check and make sure that that is correct, which it is. So I know that this right here is going to be one of the intervals for my solutions. Then I'm going to check my test point of 0. If I plug 0 in for x, I get 0. Minus 3 times 0, which is also 0, minus 4, and this should be greater than 0. So I end up with negative 4 is greater than 0. That's not true. So that is not a solution interval. And then I'm going to do my last test point. And if I plug 5 in for x squared, I get 25. If I plug 5 in for x, I get negative 15 because 3 times 5 is a negative 15. And then I'm still subtracting 4, and that's got to be greater than 0. Well, 25 minus 15 is 10, minus 4 is 6. So I end up with 6 is greater than 0, which is true. So what that does is this now tells me that I have solutions over on this side and on this side of my test intervals. So I'm going to write my solution then as x is less than negative 1, because that's going to take into account these numbers here, or x is going to be greater than 4, and that will take into account these numbers here. And this right here then would be my final answer. And again, I don't care which method you use. However, I would like you to try at least, each method at least maybe 2 or 3 times in your homework so you can get a true feel for which one you like better. So on that note, I hope you guys have a good night or good day, and I will see you in class tomorrow.